Okay, so puppies for everyone. Puppies for everyone if I don't bring the binders back on Thursday. Okay, I'm going to just do them both. Okay, so number one, there's this, so this is a 2D problem. This angle is 25 degrees. The length horizontally is 1 meter. And the height is 0.75. And external loads, there's the weight, and then there's also a horizontal force applied here to the left of 1,000 newtons. And we want to calculate the reactions. So first, a free body diagram. At the pin joint, there's a full force vector. There's the weight of, it has a mass of 50 kilograms, so this is 490.5. And then there's the 1,000 Newton force that way. And then there's a reaction from the incline. For a roller, the force is perpendicular to the surface, so this is going to be this way, perpendicular to that incline. And that's all the loads. And in 2D especially, you can pretty much, oh, let me give that a name, call that RB. You can pretty much count on having to solve 3 equations for 3 variables in 2D. So look at this. We know we're going to get 3 equations. The 3 variables are the 2 for RA and the 1 for RB, so that looks good. And let's put the origin up here. You can put that anywhere you want, and you can put the about point anywhere you want too, but I'm going to put that at the origin, mostly because that's where we have the most unknown forces. And calculate row vector, force vector, and moment. RA is at the about point, so the row vector is 0. The force vector is RAX, RAY. So there's no moment. And then the 1,000 Newton force, you just go 0.75 meters in the negative y direction. So the row vector is 0, negative 0.75. The force vector is in the negative x direction. So negative 1,000, 0. And you get minus 750 for the moment. And then the weight That's halfway along the member horizontally and halfway down vertically. So positive 0.75 for x, and then, nope, that's positive 0.5 for x because the length is 1, and then negative 0.375 y. And the force vector is 0, negative 490.5. Cross product is negative 245.25. And then last is this RB force. The row vector is positive 1x, negative 0.75y. And now for the direction of that force, we know the magnitude is RB, we need the direction. And the way I like to think about that is, here's the coordinate system. What we're given from the figure is it's 25 degrees from the positive x-axis. So this is 25 degrees from the positive x-axis to a vector in this direction along the incline. And our force is perpendicular to that. So now this is 90 degrees. So to get the total angle, you go from here, plus 25, plus another 90, so 115. Let's see. And so you get negative 0.423 RB for the x component and positive 0.906 RB for the y component. And then the cross product is 0.589 RB. Anybody have any questions about any of that? Definitely, like, the trickiest part was coming up with that RB force. Yeah? Mm-hmm. This is a pushing contact, and so a pushing contact is always perpendicular to the surface toward the chosen body. So that's how you know in this case. And that's what rollers and frictionless contacts always do, toward the body. Most likely, if you drew it like, if you drew your force like that, most likely you would get lucky in this case, and you would get an answer for that force of negative whatever the answer is. And then that would tell you that the force was going the opposite way, and it would work out fine. But it's nice to go into it knowing that that force has to be toward the chosen body, because then if you get a negative answer, you know something went wrong, you know. But in this case, since this problem worked out fine, you would have gotten the right answer that way. If we had like a big force going that way, and you did that, and you get a positive answer here, you'd have a system that didn't work the way it was supposed to work, but you wouldn't see that because you wouldn't have made, you wouldn't have made the right assumption about what that joint does. Any other questions about that right now? Okay, so we have three equations. So first, from the x component of Newton's second law, we have RAX plus 0 minus 0.423 RB Minus 1,000 is equal to 0, so I'm going to move that to the other side and make that positive 1,000. And then the y equation says RAY plus 0 minus 490 plus 0.906 RB is equal to 0. I'll move the negative 490 to the other side, and we get plus 490.5. And then the third equation says negative 750 minus 245.25 plus 0.589 RB. So I'll just write this as 0.589 RB is equal to positive 995.25. And that's a small system of equations, so you can do that without much trouble and just using substitution or whatever. Does anyone want to see me write out the matrix that you would use for reduced row echelon form? You want to see it? Okay. So we have 3 equations, so that means there's going to be 3 rows. And 4 columns. That's the 3 variables and the constant. The variables I'll do RAX, RAY, RB, and then the constant. Okay, so first equation. RAX's, we have 1. RB's, we have negative 0.423. Constant, we have positive 1,000. Equation 2, RAY's, we have 1. RB's, we have positive 0.906. And constant is 490.5. And then equation 3, RB's, we have 0.589. And the constant is 995.25. And reduced row echelon form gives you RA of 1714.76, negative 1040.39 newtons, and RB is 1689.73 newtons. And there's one thing that's easy to sanity check on this one, and that is, since you know that this is a pushing contact, that force has to be that direction, which means our RB has to be positive. So if we would have got a negative there, that would have been a concern. We would have wanted to find out where the problem was. And if there was no mathematical problem, it means the system as we have it set up isn't going to work the way we drew it up. But our answer came out positive, so that's good. Any questions about that one? Okay, and then number 2, I think, let's see. I think I'm just going to go right to the Freebody diagram, maybe. Is that what I'm going to do? That's not so hard to draw. I'll draw it. Okay, so we have a plate. And it's connected to the wall at 2 points. These are hinges. I'm just going to draw them like that. And there's another little, you can think of it as like a pulley here. The coordinate system, a couple people didn't use this coordinate system, and if you used a different one, that's fine. But the coordinate system has the x-axis that way, y-axis that way, and z-axis that way. And the dimensions that distance is 150 millimeters. I'll write that as 0.45 meters, but you could have left it all in millimeters and still gotten the right answers. I'm used to just putting everything in SI units, and then you don't have to like think about whether the units are going to work out or not. You know they'll work out. Then from here to here is 0.69 meters. From here to here is 0.09 meters. Then it's also 0.9 meters from the hinge to the other end. And it's 270 millimeters, or 0.27 meters, from where the cable connects to the plate to the end. And then the cable goes through this spot here up to a point there and up to a point here. They connect to the wall. This one, I guess, would connect right here. And those heights are both the same. And they are 0.675 meters. The mass is 60 kilograms. And there are no other external forces applied. The hinge so let me label all these. They call this hinge A, this hinge B, where the cable comes through is C, and then the rope connections are D and E, and that's all. And they say that the hinge at A, the hinge at B has axial thrust, and the hinge at A has no axial thrust. So that'll come up when we start thinking about what kind of loads are applied. And I'm going to use the coordinate system that's drawn there. And so before I start with the other stuff, I'm just going to calculate the coordinates of all these points. So the point A is just 0.09 meters in the positive x direction from the origin. So 0.0900. The point B is you have to go this whole distance, 0.69 plus 0.27, and then backtrack 0.09 along the x direction. So that's 0.8700. The point C is 0.69 in x, 0 in y, and then 0.45 in positive z. D is just straight up the y-axis, 0.675. So 0.675, 0. And E has the same Y value of 0.675, but it has also an X position of this whole length, 0.69 plus 0.27. So that's 0.96X, and then 0Z again. Any questions about the coordinates? So for B, to get this distance, you can think of you go in the positive X direction, 0.69 meters, and you get like here. Another 0.27 meters, and you get here. And then you backtrack 0.09 meters. So it's 0.69 plus 0.27 minus 0.09. And so 0.87 is what you get.
So just another question, because I did it really weird. So if I said that my about point was either A or B, and then did all the positions based on that, is that still?
Yeah, so what you did basically was you didn't use the coordinate system that was drawn. You put your own origin at A or B. Yeah, and that's perfectly fine. Or, you also could, so I'm going to choose my about point to be at that origin. But you also could use that origin for your coordinates and then choose your about point to be somewhere else, You have total flexibility with both of those two things. That's right. Yeah. Any other questions? Okay, so now a free body diagram. We have the weight force that's acting down from the middle. The thing has a mass of 60 kilograms, so this is 60 times 9.81 is 588.6. And then at the location where the cable goes through, it's the same cable going through a frictionless attachment like a pulley. And so we know that the cable is applying forces in both of these two directions, but the magnitude of that force is the same. So I'm going to call each of these a magnitude of P, but we are going to have to calculate the unit vectors going this way and that way. Okay, so we have one going like that, one going like that. We'll deal with those unit vectors later. And now we have the two hinge joints. At B, it says there is axial thrust. Okay, so let's see. So first of all, for a hinge joint, we always have a force like this and like this. Those are always there. Okay, if you have axial thrust, you also have a force like this. So we know we have those forces. And then you also can have a couple like this and a couple like this, but you don't always. Are those present in this case? They're not, because we have another hinge that shares an axis with that. So whenever you have that, you forget about these. The fact that there are two forces does everything that those couples would do, and you don't have to worry about it. And it does what those couples do more effectively than those couples do. So I'll call this RB. That's a full force vector. And then over here at A, there's no axial thrust, so there's not going to be any X component. But there is a y, and a z component. I'll just write this as RA, but you can see that it doesn't have a x component. And now we know that if we add up the variables and we have more than 7 variables, we have a problem, because in 3D, the most equations you can get is 6. We have 3 variables for RB, 2 for RA, 1 for T, so we have 6 variables, which means this will work as long as all of our Newton's law equations are useful. None of them cancel out or are redundant or anything like that. Any questions about the free body diagram? Okay, and then we also have to calculate those unit vectors for T. I guess we might as well do that here. So let's first do the cable that's going to D, or let me write that just as cable D, because they both have a magnitude of T. So the first thing we have to do is just calculate a vector that's in the right direction. Then we'll make it a unit vector after that. This cable goes from the point C to the point D. So we know that that's in the direction of the force. And so we can calculate that as the destination minus the starting point. And we've already written down all those coordinates. So that's 0, 0.6750, minus 0.690, 0.45. So that's negative 0.69, positive 0.675, negative 0.45. And then divide that by its magnitude, and you get a unit vector that's equal to negative 0.648 for the x component. The y component is positive 0.634, and the z component is negative 0.423. Yep. Yeah, as long as you use the same axis directions. And then cable E. So the vector we want goes from C to E. So we're going to calculate that as E minus C. So that's 0.96, 0.675, 0, yep. Minus 0.69, 0.45. So you get 0.27, positive 0.675, 0.45, negative. And then the unit vector is 0.316, 0.789, negative 0.526. Any questions about that one? So it's a key thing in this problem that you represent both of these as having the same magnitude t. If you did all this and you took this unit vector and multiplied it by a force like TD and multiplied the other unit vector by TE, you'd have 7 variables. You still only have 6 equations, so you'd be stuck. I know I talked to a few people who got hung up on that at least for a while. I didn't take a lot of points off for that, but yeah, that made the difference between whether it's solvable or not. Okay, so now we'll calculate rho, force, moment. For the force RA, that only has a y and a z component. The rho vector, well, since I'm choosing my about point to be the same place as my origin, I can just use all of these coordinates as the rho vector. That's sort of a nice, convenient thing. Especially in 3D, it seems to be helpful. And so the rho vector for this force RA is just 0.0900. The force vector is 0 for x, RAY, RAZ. And the cross product is 0 for x, negative 0.09 RAZ for y, and positive 0.09 RAY for z. And then the force RB, the rho vector is the coordinates of B, so 0.8700. This is the one with axial thrust, so this has RBX, RBY, RBZ. And the cross product is 0 for x, negative 0.87 RBZ for the y component, and then positive 0.87 RBY for the z component. And then that force, the force of the cable going towards D. Okay, so look at this. This can confuse people sometimes. So where is this force applied? So we're talking about the force of the cable pulling here. Think about where that cable contacts the boundary of the body. Okay, and so this cable makes contact with the boundary of the body at C, same as that other cable. It's just going in a different direction. The rho vector then is the coordinates of C. So this is 0.69, 0, 0.45. The force vector is the unit vector that we came up with before times the tension T. So this is negative 0.648 T, positive 0.634 T, negative 0.423 T. And that cross product gives you negative 0.285 T, 0 for Y, and then positive 0.437 T for Z. And then the cable going to E. The row vector is the coordinates of E. So that's 0.96, 0.675, 0. And the force vector is the other unit vector we found times T. So that's 0.316 T, 0.789 T, negative 0.526 T, and that cross product is negative 0.355 T, positive 0.505 T, positive 0.541 T. And then the last one is the weight. That's right at the middle of the plate. So the row vector is 0.480, 0.225. The force is 588.6 in the negative y direction. And the cross product is 132.440, negative 282.53. Okay, so if you scan through this, remember I said we have 6 variables. So if any of these equations aren't useful, like if no, because the row vector should be the same, yes. Did I do them different? Yep, you're right. Thank you. I just did what I told you not to do. So that the force vector is applied to the plate where the cable leaves the plate. And I think I put in the coordinates probably for E, but it's C that you need. So yes, this should be 0.69, 0.45. Okay, so I was saying before, since we only have 6 possible equations and we have 6 variables, none of these Newton's laws equations can be degenerate, useless. If we lose any of those equations, we have a system we can't solve. So you can scan down, go through these, look at all the x's. You have to have something in there and some kind of variable, or else you get an equation that just says 0 equals 0, and that equation isn't useful, and then you can't solve the system. But we have an RBX there and some other stuff for x. We have some stuff for y, and some stuff for z. So all of Newton's second law is useful. And then go to the moment equation. We have some non-zero x components. We have some non-zero y components, non-zero z components. So we get 6 useful equations to solve for 6 variables. And let me just write down this matrix. Okay, so we need this matrix to be 6 by 7. So these are the equations, 1, 2, 3, 4, 5, 6. And then we need 1, 2, 3, 7 columns. So I'm going to do it in the order R, A, Y, R, A, Z, R, B, X, R, B, Y, RBZ, and then T, and then the last one is the constant. So for equation 1, RBX's, we have 1. T's, we have negative 0.332, and constant 0. For equation 2, RAY, we have 1. RBY, we have 1. T, we have 1.423. And the constant is 588.6. For equation 3, RAZ, we have 1. RBZ, we have 1. And T, we have negative 0.949. And the constant is 0. Equation 4, T, we have negative 0.64. The constant is negative 132.44. Equation 5, RAZ, we have negative 0.09. RBZ, we have negative 0.87. T, we have 0.505. And the constant 0. And then the last one, RAY, we have 0.09. RBY, we have 0.87. T, we have 0.978. And the constant is 282.53. And then, solve that, and you get the RA vector. Well, we knew all along there was no X component. And then the Y component is 225.3. Z is 85.7. That's newtons. RB is 68.7. 68.7. 111.3 newtons. And then that P vector is 206.9 newtons. Any questions about that? Okay. Who remembers what we were doing before the break? Yeah, right. And we were pretty much done with centroids. I think today I'll just do an example problem or two, and then we'll get into structures next time. But I don't think you've done any problems yet on centroids. I don't think I've assigned any yet. Does that sound right? Yeah. So, okay, here's an example. Okay, so let's say we have a beam like that and a roller in the middle. Stop me if I already did this one, if you remember. It's been a long time. This distance is 0.5 meters. This distance is 0.5 meters. The maximum distributed load is 2,000 newtons per meter. And we're going to ignore the mass, ignore the weight. And we want to calculate the reactions. Okay, so free body diagram. There's a full force vector acting at the pin, call that RA. The roller applies an upward force, call that RB. We know the direction of that one. And now we have to deal with that distributed load. So that's a triangular distributed load. We know the height of that triangle is 2,000. We know the base is 0.5. That's meters. So the total force, the magnitude of the point force that's going to represent that is the area of this. So, 2,000 times 0.5 over 2. So that's 500 newtons. And we know that the centroid is 1/3 of the distance from the, the wall side of the triangle or the point side. So 1/3 of 0.5 is 0.16 repeating. So we know that this distance is 0.16 repeating. So that's a downward force with a magnitude of 500. And this distance is 0.16 repeating. This is just a single horizontal beam, so I usually don't do the row and the force in the moment, but you could do that. So let's just go straight to Newton's second law. What are the forces? RA has two components. RB is just in the positive y direction, so 0 RB. And then the 500 is in the negative y direction, so 0, negative 500. And that's equal to zeros. And then the moment equation, I'll use this as the about point. So there's no moment produced by RA. What's the moment arm for RB? Well, we're just on RB right now. So for this force, it's just this distance is 0.5. It's the next, yeah, right. So we have a moment arm of 0.5. The force is RB. And now we have to think about the direction. Would that force make it rotate clockwise or counterclockwise around the about point? Counter, so this is positive. And then the moment arm for the 500 is 0.5 plus 0.16 repeating. So that's 0.6 repeating. The magnitude of the force is 500. And would that force make it rotate clockwise or counterclockwise? Clockwise, so that's negative. And then those are equal to 0. So I think this should end up being, so RB is equal to 666.6 repeating, right? Yes. I'm always afraid I'm going to come back from like a break and not be able to do anything anymore. Yeah, right. My brain's older. And so then RA has 0x component, and it's equal to negative 166.6 repeating y component newtons. Okay, so in order for this to stay in equilibrium, notice, so we have this RB pushing up and this RA pushing down. So in order to keep this in equilibrium, if this force is pushing this way, kind of trying to make it rotate around this roller, you have to counteract that by applying a downward force here, even though the net effect is just to counteract the downward force. Any questions about that?
I just, on the next exam, when we're dealing with centroids, are we going to need to remember however many equations you gave us?
Oh, like the formulas for the shapes?
Yeah.
No, that'll be on there. Yeah. Any other questions? Okay, I think we should ease back into this, don't you think? Back into, okay. Yeah, let's go. Maybe Thursday will go a little longer. Okay. I don't want anyone to hurt their brain, especially me.